Lab and Department of Social and Political Science. And today I will talk about, I say, a provisional way of, in particular, estimating parameters in agent-based models of social networks. And also what Fede was referring to before, also of an observed mechanism or complex nonlinear type of mechanism that might impact some network-related phenomena. So okay, good. I mean, which is something that is very valuable in its own right, yet we can do something more, right? So the perspective that I want to sell you today is that we can use a conceive agent-based model not simply as dynamical simulators, but also as statistical models. As I told you, they have these Janus-phased characteristics. In particular, if you, care about going back in the statistical literature, you have this nice paper from Deagle and Grant in 1984, in which they describe what they are called implicit statistical models, that are models that don't have tractable likelihood functions, so cannot derive asymptotics as many statistical models do, but still they are parametric, so you have some parameters governing the outcome and the inference that you can make. They are stochastic and then can generate data. So you can, in theory, use them to actually test hypotheses in more sophisticated way that would do with standard statistical ones. In particular, you can do you can perform the two typical inferences procedures that whenever we want, we have a statistical model we want to perform. That is, we can validate the outcome of explicit fine-grained behavioral mechanism against empirical phenomena, what's called typically goodness of fit test, but we can also recover the parameters of the fine-grained behavioral mechanism from data, also having some uncertainty measures. So if you are a frequentist, you can, for instance, carry out hypothesis testing. On Bayesian, you can do your own credible intervals, whatever you want. So this presentation is about, in particular, this aspect. I will briefly mention about goodness of fit in the end. And to give you some perspective, we will need some special care, okay? Because in agent-based model, we typically have three issues that render them a beast in terms of typical statistical procedures. We have intractable likelihoods, and very often we cannot even write down the factual form of the likelihood. Second, the parameters refer very often to unobserved mechanism or mechanism that we don't leave traces if we if we follow the archaeological traces analogy. And finally, we might also have latent or unobserved agents attributes that can interact with this unobserved mechanism and complicate the issue. So I will, okay, despite this challenge, we can still develop solid routines. I will give you an example from this paper in which I'm collaborating with Federica and with Elisa Bellotti from University of Manchester and the Mitchell Center for social network analysis. So this model is about network affecting behavior, or as you typically say, social influence. So it's not about network formation, not about the coevolution of networks and behavior. This is a simple step how networks features say impact something, okay, some characteristic of individuals. In particular, the goal of this work is to understand the spread of malaria preventing measure, and in particular, this will focus on a protection cream in 10 rural Indian villages in this region. It's called Meghalaya. It is situated in the north of India, close to the Himalaya region. So it's a very, I mean, you have the big mountains in here, so it's very hard to reach. So it's a very hard to reach population, also with infrastructure. The government has some troubles going there. You don't have roads, but at the same time, you have also a lot of tropical rainforest. So you see, individuals are mostly engaged in agriculture. So you do have a lot of mosquitoes, and so you have a high malaria prevalence. In particular, the idea is that to study the adoption of this protection cream, because the government, the Indian government, has been able to reach a high adoption rates of in-house anti-malaria measure, for instance, like bed nets or any type of anti-malaria measure that you can use in your own house. But here people mostly live outside, and in particular males commute across villages to work in agriculture, in rice cultivation, and exactly there when they get bitten. Yes. And I mean, and they don't use protection, right? And one of the most useful protection is this cream that nonetheless is not distributed by the government like the bed net, but they must buy this at some local market, which is also is not fixed in one place. So they have to travel to the market, buy the cream, and then use it to go out to load. Okay, so it's something where, I mean, social influence can play a role in here, right? Okay, we will particularly try with this empirical case that I'm going to present to fit this 12.5 adoption % rate for the biggest of these 10 villages, but ideally we will do this also for other protection measures, not just for cream, and for every village. Okay, therefore, to do so, we defined an explicit behavioral model before fitting it to data. Okay, so we didn't try to make inferences about the behavioral models from the data itself. So we reason about what, how could this influence process work in this region, also leveraging on the qualitative insights that Elisa, that actually carried out the data collection, gave us. And then we try to fit this model to data and to estimate the parameter of this. So, well, social influence implies the decision to buy and use the cream is influenced by the relationship that these villagers have. And in particular, we believe that this influence is not what's typically called in literature simple contagion, like that of infectious diseases, in which I just need exposure to someone with a disease to actually be infected, but what's typically called complex contagion, as defined, for instance, by Damon Sentol and Michael Macy, because it is very hard for these individuals to understand the efficacy of this chemical product. Also because typically for health-related issue, they revert to a traditional healer that uses, I mean, herbs and some like traditional medicine, and they are kind of skeptical about using chemical products for health preventing measures, right? And therefore, it is likely that these villagers will need reinforcement from multiple sources to adopt it. Okay, so it's not that just my peer is using the cream, but if instead, if I have, I don't know, 4 or 5 individuals that I'm relevant for myself that are using the cream, then I'm more likely to have to jump in and using this cream. So you have a threshold effect, but this threshold is not set to 1. So I need at least, I don't know, a given number of individuals, and we try to recover this from network data in order to adopt this measure. So the research question that I'm trying to sell you today is that can the adoption rate be explained by this complex contagion mechanism? Which, just to give you a visual interpretation. Here you see in the vertical axis, but you don't see anything because I don't. But here is the adoption, okay, which is a binary state. I'm not adopting, then I switch and I start to use the cream. And as long as I have a given number of my contacts that are below this threshold, in this case A, I do not adopt it. Whenever I hit this threshold, I start adopting, right? Okay, so who are these contacts? This is the data that Elisa and her team collected in these villages. Here on the top, you see positive ties. These are individuals with whom these villagers speak about health-related issues. They can be both how should I protect myself, something like this, and also to like health-related gossip, say, hey, did you hear this individual is sick? I mean, something that people do, right? And here you also have negative ties, that is with whom you avoid speaking about these health-related issues with. You see that in both networks you have an hub, okay, someone that is very central in these two networks, and these are two very different individuals. The hub in the positive ties is the traditional healer, okay, and the hub in the negative ties is what's called the ASHA, the accredited social health activist. That is a government figure that goes there trying to persuade individuals to adopt malaria preventive measure. And so you see a lot of villagers do not talk with the official source, say, but they talk with the unofficial one, the traditional healer, whom they trust. Okay, on these networks, then we define these are behavioral mechanism. We formalize it in a computer algorithm, in which we do the following assumption. For the ASHA, the government official, and the healer, we consider as zealots, as they are typically called in the opinions dynamic literature. That is, they influence others, but they are not influenced back. Indeed, clearly the ASHA adopts every measure, or yes, it adopts every measure, and the healer does not adopt anything. Then what we did is that with respect to the other villagers that are the object of influence, the one that can actually be influenced, we simply randomly selected them one at a time. And we suppose that they continuously and dynamically calculate the probability of adoption, okay? And we suppose here as a logistic function of certain network feature, which can either be observed or unobserved in our own data. It is important to understand that this whenever they adopt, they can stop adopting, okay, if this condition ceases to exist. I mean, if these conditions that are embedded in our network feature are not met anymore, then I can start to not adopt anymore the cream, that is to not put myself the cream. So this is just a functional form, it is a logistic function. And importantly, what we wanted to do is that we wanted to recover this beta k that weighs the network features, say, which can be considered in this logistic regression framework, say the importance of network feature k in explaining the probability of adoption, controlling for all the other possible behavioral measures. And I mean, we estimated every of these parameters, but for us, the inferential goal is to recover the unobserved threshold, okay, the number of contacts that I need to start adopting, and the beta threshold, that is how much this complex contagion effect mattered in the probability of adoption, net of the effect of the other network features. So this was our target, as well as the relative weight of this mechanism on the probability of adoption. Well, since ABM can be seen as a statistical model, we can also do and we explicitly formalize the causal mechanism that then will generate artificial data, which we will compare to empirical data. We can also use typical instrument of causal inference, for instance, here directed a cyclic graph. Simply, what we want to do is that we want to estimate the net effect of the threshold and the importance of this threshold, complex contagion-like mechanism on the probability of adoption, by controlling for other network features that can impact both. And these network features in particular are, well, a baseline tendency to adopt, as they typically done with, for instance, in sound modeling, a tie with the ASHA, okay, that is the government official, a tie with the healer, at least one negative tie, and household prevalence, because we also have household data, I mean, kinship network basically, and we calculate the probability, the average prevalence of that adoption, of the cream within a given household, and then this is another confounders. Now, how to estimate actually these parameters, because it's pretty hard, because we don't have any data about these thresholds in the population, and clearly we cannot have any data related to this effect. So we employed what's called, and it's not actually a very recent development, but it's still 15 years, 20 years ago, it's called approximate Bayesian computation. That is a way to fit complex statistical models, in this case, from information-based networks to network data, to data in general. So we start typically with an observation, okay, from which we can either retain the full distribution, so we can use this full distribution as our empirical target, or compute some summary statistics, okay, from this distribution. In our case, it's simply the adoption rate for this provisional example. Then what we do, we will have a prior distribution for each of the parameters involved in the model. We will randomly sample according to this probability distribution vectors of parameters. We will simulate the dynamics under these conditions, and we will define a distance matrix between the artificial generated data and the observed data. Or the whole distribution, or the moments, or the sufficient statistic that were selected. We will specify a tolerant threshold. There can be even 0. Therefore, this actually basically gives us the precision of the estimates that we want to achieve. And then the parameters that will be, so this will be the parallel realization of our simulation procedures at different priors. The one that meet this condition are retained and will form our posterior distribution, which under some reasonable assumption, we can be guaranteed that we will be the true posterior distribution of our parameters. Actually, what I showed you is typically called rejection sampling ABC, which is very inefficient, as you see. And therefore, what we are actually implementing is a more refined version that is called sequential Monte Carlo, but it's just, fancy labels. It is a form of importance samplings. That is, we will start from our prior distribution, we'll draw parameters, we'll simulate the model, and we'll try to compare it with empirical data with a given threshold, okay, with a given tolerance bound. Then we will keep the retained parameter as before. We will build instead a proposal distribution out of this parameter with some kernel density estimators. We will draw from this proposal distribution. We will compare against, simulate the model, compare against the empirical network data now using a smaller tolerance threshold, and we'll iterate this for a given number of generation. And this is again guaranteed to reach to the true posterior, at least whenever this tolerance goes to 0, which is typically not the case empirically, because it's very computationally burdensome, but at least that's what we are sold. Okay, so now we're going just to show you some conclusion we can derive. So with respect to the priors, we follow in our model, and this was my suggestion, the general principle from the Stand developing team, for instance, Andrew Gellman and colleagues, to use what's called weakly informative priors. That is the idea that the priors rules out unreasonable parameter value, but is not so strong as to rule out values that may make sense. So this is what we employ as our principle for this analysis. So we excluded very unrealistic possible parameter value, say a threshold of 27 or something like this, or negative threshold clearly, but we restrict it to a bound, and then we give it a bit of space to search for possible solution. And this, for instance, this is very provisional. Okay, this is actually, I generated it 2 days ago, but this is what you can obtain. For instance, you can obtain inferences about the posterior distribution. This will be discrete because the threshold will be a discrete number about the threshold here. Okay, so you see that likely you need between 2 or 4, most likely 3 individuals in the population to start considering adopting the cream, okay, for this social influence process to take place. And how much this threshold then impacts translate on the probability of adopting. So here we can derive, for instance, the posterior for the data threshold, as they called. Here you see these are called the 95% credible intervals. For instance, what you can do is you want to test whether this is 0, then you can look at what is the probability that this effect is not there. or if you want to do more sophisticated hypothesis testing from this distribution, you can still do this. Remember, this is controlling for all the other network features that we have implemented in our. Well, how do you know this? These are valid inferences. What you do is that you compare what are typically called in Bayesian statistics, posterior predictive checks, and also you prior predictive checks, and so you can perform this. So, for instance, here it's the result, the adoption rate in this village arising from sampling 1,000 randomly selected prior vectors of parameters, simulate the models, and see if this is the more widespread probability of adoption. And this is from our model. So this is the best fitting, from the best fitting parameters in this ABC sequential Monte Carlo. And you see they are on average closer and closer to the true adoption rate in this village. So the inferences are empirically anchored because they reproduce on average the empirical adoption rate much better, for instance, than what the priors did. So to conclude, I hope to give you a glimpse of how these new techniques can allow us to estimate parameters of fine-grained complex algebra-based models from even observational data, even when we don't have data themselves related to these characteristics. For instance, in this case, what we did is that we estimated the threshold for an observed complex contagion process and its impact on the probability of adopting a cream to prevent mosquito bites in rural India. This is a work in process, but it's promising. And in particular, I think that it is promising because we don't need to specify necessarily implausible behavioral assumption for analytical tractability of our agent-based model to then be fitted to any type of data that we wish, in this case, network data. And we don't have to give up on the possibility to test the effect of unobserved latent network processes on network data. To have the real conclusion is that we also try to work on, okay, this is an example of how you can have a goodness of fit test of agent-based model on empirical data. It is a paper that Federico mentioned together with Flamini as well, where we basically wanted to start from a sound backbone, relax some assumption, introduce more fine-grained and observed mechanism of network formation for an advice-seeking relationship, also leveraging on observed attributes like skills or threshold of cognitive overload that weren't present in the Lazega network, and in which we basically derive a routine to then test the implication on the artificial network in itself by following a procedure that was outlined by Christian and Tom Snyder's in 2015 paper. So we can do also goodness of fit. And the next step is also trying to recover parameter in these models, because I mean, we had a kind of artisanal routine in this case, okay, because of different constraints, particular time constraints. But I mean, this is the next step that we are trying to follow. Thank you.
Hey, Francesco, any question for the?
Yeah, Francesco, you showed us at one point the posterior distribution for beta, for beta coefficient. That's it, yeah. So this is the beta coefficient for the effect of number of neighbors.
Yes.
That have adopted.
Yes.
On the probability that you adopt.
Yes.
Right. What I'm not getting is the threshold. Doesn't the threshold imply a different probability function entirely? Because with the threshold, you don't have the effect of a continuous independent variable, the number of neighbors who have adopted, but you have a situation where once the number hits 2 or 3, probability of adoption is 1. So I'm not seeing the previous graph, how you get there.
Yeah, yeah.
Is the threshold also a parameter?
Yes, the threshold is a parameter. Yes, technically, okay, yes, right. The threshold is a parameter. Technically, how we implemented this is an indicator function that is basically a condition that you check how many of your neighbors have adopted, okay? And this is how many is a parameter that you can recover from this inferential procedure.
Right. Isn't it either or? So either you have a continuous effect with the beta, or you have a function with an indicator function.
No, well, this continuous effect is activated only if you have non-zero threshold. Okay, So it's a weighting, okay? You have in the formula beta threshold times an indicator function that tells you how many of your neighbors have adopted. If the number of neighbors that you have adopted surpasses a given threshold that you need to recover as well from data.
Okay, so once the
threshold is determined, you see how much this impact that threshold on the
so
probability.
it's not a threshold in the sense that once it's hit, probability is 100%.
No, exactly. It's a condition that you need
It's
to
more
satisfy. Yes, better to say a condition you need to satisfy.
How does this relate with Tom Valente's threshold model and specifically with the idea of early and late adopters? So in that case, the argument is that really there's some people that will be adopting early and others that will adopt late. As I understand it, you only have the results after, right? You have only the people that actually adopted. And there's, what is it, 20%, 30% or something?
5%.
5%. Well, 12%. Okay. So is it, is it like a S curve that you would?
We don't have longitudinal data on it, unfortunately.
No, but are you assuming an S curve in that way? How is the behavior over time? If you look at it from the time perspective, is it like an S curve that is happening, or is it like things? Yeah, I'm trying to understand.
In the model, in the data.
In the model, because in the data you don't have it, but in the model.
Yes.
Do you have any information on that?
Honestly, no.
Okay.
I mean, I'm pretty sure that we did. I don't know if you
I have the model here, but I can't show everybody.
Okay. I didn't check it.
Okay.
But it wasn't much of an S curve.
Yeah, possibly not.
No.
You could have a dynamic threshold.
Good at dynamic threshold as well, yes.
Yeah, so that probably be able to.
You could also have a heterogeneous threshold if you wanted to model
Yeah.
that situation that Phil
Yes.
is talking about, right? Early adopters, late adopters, so people who require a lower threshold or a higher threshold.
Yes, then you will have, say, another meta parameter that is how many early adopters you have.
So the message is that even at this level of complication, this is actually a very simple model,
Yes.
even if it looks so complicated.
Jen.
I don't know if we have enough time for another question, but
Yeah.
I just wanted to ask whether, I mean, you're fitting to the proportion adopted. Are you looking at the shape of the people who've adopted? Like, does it look realistic in other senses in that they're not all clumped together, or they're spread out throughout the village in an empirically realistic?
Yes, we will. This will be the next step. So this is, say, the baseline test that we did. Okay, but this will be the next step. We also have data clearly on who adopted. Okay, actually who and their connection, and we can reproduce the whole network. We try to feed the whole network with who adopted.
I think it would be a very an impossible test to get the right people to adopt, but I'm thinking more about the clumpiness of
Yes.
the adopters.
Yeah, that's true. Yes.
Okay, any other question?
Yeah, please, two short questions. I have short question. One is related to what Rafaelis asked about. So I can imagine making it more complex. For example, that people have individual thresholds and so on and so forth. But I was wondering to what extent you have enough information in your data to estimate all these things.
That's true. Yes.
So if you can give a kind of a glimpse into, okay, how close you are already to the boundary of actually identification of all these mechanisms.
Yes, that's true. That's why complexifying the model, in this stage, I think it won't help because we don't have such fine-grained data. But I mean, with respect to this, what relates to the previous question, to the adoption rate, this is a very coarse-grained measure. Okay, this is the first step. We are, I mean, we're pretty well reproducing the empirical one. Okay, so with this model, which can then be, if we had more data and possibly longitudinal or more fine-grained, we could also define different set array of summary statistics, such that then our model will be better. We can better claim that it identifies.
Which I don't believe it's the case.
Yeah, no, it's not.
Given the
So the second
data collection.
Yeah, so the second question was, so given the amount of data that you have and this complex model, what's the kind of time complexity of estimating this? So it's like, how practical is this approach?
Well, if you use parallel computing, I mean, then it depends. But in this network that is about 100 people, 93 takes about doing an extensive exploration a couple of hours right now using Python. So maybe if you have some more efficient routines like in C++ or Rust, might take even less.
Okay, thank you, Francesco. Now we have Jen.
Slides should be there somewhere.
So, Federico, it's already there. Ah. I want to read you something.
That would be a problem. Can you just check that that's that's not visible? Excellent. Hi everyone. For those who don't know me, I'm Jen Badham. I'm at University of Durham, which I've just been asked is where that is. It's northeast England. Okay, for those who are familiar. Today I will be talking about putting social structure into artificial networks. This is work I'm doing with Christina, who will be talking later about some other work, and it's funded by the Research Council in the UK. So this comes from a slightly different perspective. Flaminio earlier was talking about the fact that there's sort of two communities with the ABM and the network analysis, and you know this workshop is bringing this together. But there's also two communities within social network analysis, and in fact also two communities within ABM, and that's the computational science community and the social science community. I think pretty much everybody in the room is a social scientist and would think of themselves as a social scientist. Is that almost true? True, almost true? Okay, but there are very different questions that come from those two perspectives, and this is a quote from Organised, who's a social scientist, talking about the different types of problems that computational scientists and social scientists want to think about with social networks. And in particular, social scientists tend to be a bit more empirical, looking at this particular network, trying to understand the influences within this particular network. Okay, so this sort of social dynamics question. Computational scientists tend to ask a more general question about, you know, ensembles of networks. What are the features of different types of networks or so on? But those two different perspectives come together, particularly in network diffusion, social dynamics, so dynamic processes over networks. That's also where ABM sits nicely. Okay, so we've got this common interest of how do network properties affect diffusion outcomes. And, you know, an ABM is just a simulation of a process. We have an explicit mechanism of change. We've got things like autonomy and interaction. Okay, so this is just setting the groundwork with stuff you already know, but possibly not quite from that perspective. We have very well established idealized behavior change mechanisms. We've just seen a paper about complex contagion. Okay, where you've got this threshold either of a proportion or of a certain number of neighbours. Once that threshold's exceeded, then there's some probability of this person. You know, this person has a couple of neighbours who have adopted the behaviour. They've got a probability of adopting it themselves. Then there's this other type of simple contagion where this person has already adopted. The people who are their network neighbours have a chance of adoption. Okay, so those are idealised processes of contagion. The question is, do we have the similar sort of resolution or fidelity for networks? Do we have idealised networks available that we can run idealised contagion mechanisms on to understand the effect of the network structure on the diffusion outcome? Okay, and this is the question that we're working on. So empirical networks don't really allow us to make general claims about how network properties influence the diffusion over the network. We know that, you know, within that network, the diffusion looks like that. But how then do we extrapolate that to say, you know, that in general, something like, well, we know, for example, that if you've got higher density, then you know, in a simpleton page, and you'll spread. That's a mathematical result. But we can't extrapolate from a single empirical network to talk about what are the features of that network which drive different types of diffusion. Okay, mathematical analysis requires very simplistic networks, and real social networks are just not that simplistic. They have much more structure. So what we are doing is trying to get to that. Well, we're not going to get to that answer. We're trying to do the groundwork to make that answer possible later. So we're looking at a bunch of different papers that have algorithms in them for constructing more realistic, but still artificial networks. Okay, these algorithms typically have multiple mechanisms in there. They typically target one or more network properties. We're trying to collect that into some sort of information source that says these sorts of mechanisms are available to create networks that allow you to have realistic values of these sorts of properties. That's where we're going. So we're in the collecting and classifying. There's three broad schemes. You will all be very familiar with this, I hope. You can start with a set of nodes and add edges. So, you know, the classic example is the Renzini, where you start with your nodes, you go through each pair of nodes with some probability, create an edge between them. You can grow the network. So you start, the classic example here is preferential attachment, where you start with some sort of seed network, nodes and edges, and you're adding nodes and edges, you're growing the network. And on the button, and again, the node comes in, picks three edges, nodes to attach to. Next one comes in, picks three nodes to attach to. You know, this is just growing the network. And the third is that you start, this is also a classic example, what's Strogates. You start with some sort of network and you rewire it in some way. In this case, you go around each edge, decide whether to rewire it to a random edge. Okay, so those are the three starting points. So far, we've looked at a little over 100 papers, some ridiculous number of papers. Christina has done most of the slog work on this, by the way. So we've identified 8 mechanisms that we're still mucking around with, you know, solidifying the classification. And they're sort of, you know, your stochastic type thing of some sort of probability function, some distance function, spatial, social network type things, configuration model where you're starting with a target degree sequence and you just construct your edges from those. The cumulative advantage, not just the degree, but different types of attractiveness, you know, fitness type things. Network neighbours, as you grow your network, instead of attaching to this node, you select a node and actually attach to the neighbouring network, neighbouring node, so as to promote clustering. Grafting, where instead of you adding a node, you're adding, you know, some sort of small configuration or motif. And rewiring, that we haven't decided whether or not that's a mechanism as well as a starting point, but that there's quite a lot of targeted rewiring, often using some sort of Markov process where you sort of say, you know, you do trial the rewire. If it improves the value of whatever property you're trying to get to, you accept it. Otherwise, you reject it type thing. Okay, so each mechanism can be combined so that you can get multiple mechanisms in the one algorithm. And what I'm going to do is just go through spatial distance to give you an idea of some of the richness of these mechanisms. So the simplest form of using spatial distance is Gilbert's plane networks, random plane networks. And the idea here is that you know, uniform distribution, distribute your nodes in space, and basically everybody has a fixed distance, and it's the same distance. Any two nodes that are within that distance have an edge between them. Further apart, they don't have an edge between them. Okay, and so there's one parameter which is that distance, and obviously, as you can't really see it, but there's solid lines here, and there's dashed lines here from Gilbert's original paper. As you increase ours, you increase the distance that, if you like, the agents can perceive from our perspective. Then you get a denser network and a less fragmented network. And this came from communications where it was really about, you know, things like, well, 1961, so it's not mobile towers, but are the mobile phone towers close enough together to actually allow messages to pass? Yep. So that's the simplest. As you increase R, it becomes less fragmented. The next one went kind of the other way. So here we have a regular lattice of nodes, and you have a more interesting distance function. So it's a probabilistic distance function. Two nodes that are close to each other are more likely to have an edge, not guaranteed. And even nodes that are quite some distance apart can have an edge between them. That's what this diagram is supposed to show. So you've got your regular nodes. This particular node is looking at the distance. This particular node is sort of constructing probabilistic distance functions, and you can see that, you know, some edges are created close in, and a few edges are created a bit further out. The magenta dots are the ones that it will create an edge with. Okay, so that's the opposite way. Regular lattice, interesting distance function, and that this has two parameters: the overall density, you know, of edges, and also the preference, the weighting between long or short distances. It's a bit more complicated than that, but we'll pretend it does have two parameters. Okay, so the next step is to put those two ideas together. So now you have random locations, so varying density of points, plus an interesting distance function. But what Keeling did was to add focal points. So you're not just relying on the fact that randomly distributing points leads to varying density of nodes. What you also get is you add in these focal points and you push the nodes towards their closest focal point, and that exaggerates the density differences. Okay, so combining that with this distance function, you're able to control for more properties. You get higher density where close to a focal point, and lower density when you're away from a focal point. And at this point, we've moved away from communication networks. We're now very much in social networks. This was actually for epidemic modelling. And what Keeling was trying to do here was be able to target either clustering coefficient or assortativity. You can't do both, but you can get one or the other, as well as edge densities and so on. Okay, then there's two other extensions. Lennartson and colleagues chose some of the nodes to be focal points. Instead of using focal points as sort of a second layer, chose some of the nodes to be focal points, and then had a differential probability that said, okay, if it's a node and a not node, then multiply it by a scaling factor, multiply the edge creation probability by a scaling factor. If they're both nodes or both focal points, then don't. The idea here is that you're getting hubs in your network because you're getting much higher proportions of edges that are a focal point and a not focal point node. And so they've actually been able to separate clustering coefficient and assortativity so that you can target both of them. The other one that's a bit different is Hamill and Gilbert, different Gilbert. This one's Nigel. What they've done is they've actually done it from a very agent-based modelling perspective, where what they do is they distribute, we've gone back to a regular lattice, but it's not complete. So only a proportion of the lattice is filled, and each node is an agent that has its own fixed distance, and basically two nodes form an edge if they are closer than the minimum of the two agents' distances. Okay, so gone back to that regular grid idea, but with spaces in it. Okay, so that was a very quick run through of one of the mechanisms. What we're trying to do is assemble all of these to say how they can help us with this problem of we don't have idealized networks out there that look close enough to real social networks to be able to do social science questions on. Computer scientists quite regularly do papers that say, oh, here's an interesting diffusion process, let's run it on Erdos, Renyi, Barabasi, Albert, and Strogatz, and say, oh, look, here's a general conclusion about diffusion. Now, those networks don't look anything like social networks. And if we want to be able to, as social scientists, if we want to be able to make similar conclusions in a social science meaningful way, then we need networks that are realistic enough, but that we can still vary so that we can still make robust simulation sets to make claims about about how network properties that matter to us affect diffusion processes. One of the things that we're doing, and this is very preliminary and won't look anything like this when we actually finish it, is look at, here's our mechanisms, here's our target properties. So these mechanisms are embedded in papers where they're trying to create a network to get some realism on one or more network property. So this is basically a heat map of which properties are most targeted by which mechanisms. You can see that pretty much everything wants degree distribution. That's kind of or degree sequence. That's kind of a fundamental that we want the degree structure to look like. Quite a lot have been targeting clustering coefficient. The spatial distance ones, you can see from this, are some of the more popular. That's been used a lot. And the rewiring picks up assortativity, degree distribution, and geodesics, for example. So that's kind of saying, well, if you want a network that has these sorts of realistic properties, then here's a sort of mechanism that you can look at. The other thing I wanted to point out, and I do have enough time, is that some of the properties are interdependent. Okay, so if you push one property, you might be pushing another. Okay, so this is a paper, Hong Zhao, that looked at 4 networks, not social networks. They're things like metabolic gene function and so on. And what they found was that assortativity and clustering coefficient are positively correlated. That they were exploring the property space. They started with the degree sequence, rewired so as to increase assortativity, rewired so as to increase clustering coefficient, and looked at the way that the two properties were related. They also found that those two were positively correlated to, positively correlated, negatively correlated with geodesic, except for one of the networks. So we are doing something similar where we're doing some rewiring. And we're also finding that assortativity and clustering coefficient, this is just one particular social network, which is about co-membership of boards. Assortativity and clustering coefficient are related. And geodesic gets in there as well, but it's not a really general principle. So that relationship is conditional on where you are in the property space. Okay, so here we've been pushing assortativity up, and we don't start to get a relationship with clustering coefficient until we're in quite high values of assortativity at 0.4. If we push clustering coefficient, we never get that relationship between assortativity and clustering. And this particular one, the geodesics, didn't really get pushed that much. It's too small a network. But so we're also exploring how properties are coupled or able to be uncoupled, so that if you do want to create networks that are realistic on this property, whether you also have to worry about some other properties. So I would argue that to study diffusion at a general level rather than a particular network, the networks have to be represented at a similar fidelity as you're representing the diffusion process. You know, ABM needs to represent the whole thing as at an appropriate level of representation of quality of matching. We have a lot of work. The first step is finishing this mechanisms classification, publishing the taxonomy. We're always looking for more papers. As I said, we do have over 100. We are about, almost at the point we're going to put the list up on a website to say these are the papers that we've looked at, and we'll have some sort of submission form to say, hey, have you found this? Have you found this one yet? We're planning to implement some of the more interesting algorithms for general access. Part of the reason that computer scientists in particular tend to do, compare those three networks is because those are the ones that are built into Python and R and so on. So we want to add a few to that standard library of things of networks that you can create. We want to fill out that property mechanism map. And we want to sort of document or create some more flexible generators so that these tools are available to the agent-based modelling community to say, okay, here's a diffusion process. Let's pull out the right sort of network so that we can look at how these things relate. I don't think we'll get to the case studies bit, but we can try. And that's it.
Good timing also. Any question? Yeah.
Thank you. So, have you considered looking at the literature on spatial analysis? Because there's a huge literature on how to generate segregation patterns.
Yes. Yeah. I'm lightly familiar with it, but no, we haven't looked at it in detail. But yeah, that's an interesting idea of thinking about how the segregation or diffusion, spatial diffusion, work in spatial networks. The spatial ones that I'm familiar with tend to basically be cellular automata. Like here's the process spread to the neighbours. So if there's a particular paper that you think is richer than that.
Won't ask me that. Okay, what papers are you thinking of? But I will have a look at my thing. But I know that they are trying to simulate segregation patterns with either, starting with focal points or also rewiring or removing agents or whatever.
Right. Yeah, so I'd be very interested if you can think of the right person, the right author or paper.
I think there are mostly packages that do that, right? So that's was a second point. I think you're looking at papers where people do this, but I think there are a lot of algorithms and packages that do that and don't have a paper with it.
Yeah, we have been looking at software as well. So I didn't pull that up.
Your analysis is focusing on undirected networks, right?
Yes. In fact, simple networks, undirected networks without loops, that with a single edge. Though we are noting that a couple of the algorithms do bipartite networks, for example. We are noting that, but we're focusing on, I guess, the easy case first.
I was thinking of the bias net models.
Yeah,
Think about Scavorts and Ferraro originally, where they actually have these reciprocity bias and the sibling bias and all these things, which are very local ones, which are far more closer to the ergo models.
Yes.
And the local processes where, that
We
are
have
generated.
them tentatively in our stochastic mechanism box, but I need to do more work with them because they're not something I'm aware of them. You've told me about them before, in fact, but I haven't worked with them, and so I haven't really got a feel for how the networks get constructed in them.
And it's more directed
Yeah.
as well. So
That's okay.
for undirected.
Yeah, that's okay. We are focusing on the undirected, but if something's only about directed networks, then we'll put it in.
Last question, Francesco.
Yeah, it was very related to the Philip one. Have you considered with respect to the goal of generating network with some specific features, having also interdependencies among themselves, have you considered in your taxonomy the ERGMs, the exponential random graph models, which can also be used to simulate networks?
Yes. Yes, so ERGMs is in our stochastic class.
Short question, short answer.
Yeah, okay. So you showed these scatter plots in which you can characterize the distributions of networks according to all the various properties, like community structure and so on. And you can say, okay, we can kind of pick a proper mechanism given that we want to pinpoint a particular property that will be realistic. And I wanted to ask a kind of a provocative question, for which I apologize. But how do you know what is realistic in this big distribution of, say, community structure and some other property?
I guess that's an empirical question. Like
it is, yeah. But we don't know, right? So it's like if we imagine a COVID-related contact network, we have no idea what's the granularity, say, of that network.
Yeah, fair enough. But I think that's a different question for a different researcher. That's all. But I do think that we can at least say, well, we want networks that are like this empirical example. I don't think that we can talk about empirical classes of networks. So we can't say that, school networks, for example, typically have clustering coefficients of between this and that or anything like that. They just vary all over the place. But we could say, here's a network that we're modelling a diffusion process over, and we want to make claims about what are the important properties within that network to make that. Now, we could fit an ergom and use goodness fit type stuff to try and say, okay, let's get some other networks that are similar, but this is allowing an outside fit to that sort of network and say, okay, well, what if we just vary in sortativity and hold the other properties constant? How does that affect the diffusion? That's where we're trying to get to.
Excellent. Thank you, Jan. Christoph?
Dan vooral ook meer email.
Emails of my collaborator. That's a policy.
Appreciate your attention to my privacy.
Yeah.
I mean, you might have to open the window there. It's like I mean, like hot flush myself or just like yeah. I'm just saying, it's a fun. I'm insane. You can get one as well.
It's your Spanish.
Yeah, it's a Spanish to be up just there, like yeah, there you go. Yeah.
Su control, no, ma non riesce su.
Vabbè, uno da quelli. Doing the same thing, right? We're at 11.
So they did before that, at least this.
Several dimensions. You want to tweak only one dimension,
Yeah.
right? But yeah.
Well, thanks for the invitation. Thanks for getting the presentation started, Federico. Well, my name is Christoph, and I'm going to present mostly an empirical paper, not so much meta level topics, but I'm going to do a little bit of meta level because I felt it was expected after the first few talks. But then I'm going to zoom into something very concrete. So in a paper together with Kieran Mappin and Andras Varish. So what we do in our research group at the Social Networks Lab is a lot of empirical networks research. So we work with these very messy network data that look like this, for example. But then it's always a combination of empirical work, of theorizing, and also statistical methods, how we can actually answer certain questions that we derive from theoretical arguments. And I'm just going to give two short examples for the meta part of my talk before I'm going to show the Coleman boat, which I added to my slides. And then I was disappointed that no one else showed the Coleman boat. But anyways, here we go. So this is an empirical network of friendship relations in a adult housing community. So these blue ties symmetrize are friendships between people of different genders, which are indicated by the shapes. And then you have a different type of relation, which is marriage or long-lasting cohabitation ties. And those two networks coexist. So the marriage ties, they are somehow a part of the cultural context or the context under which individuals then form ties. So they usually, for example, agree with their partner on their friends. They often couples befriend other couples. So there's certain things that are actually determined by those dash ties. And what is very interesting, if we can study those micro-level processes, trying to understand under what circumstances is it more likely that a tie is being formed. Our hypotheses were mostly about the embedding of those marriage ties. But what is actually interesting, if you zoom out and look at the network as a whole, it is somewhat clustered, and these clusters follow ethnical and religious attributes, which is somewhat surprising because this is a very liberal community. People claim to be very open-minded, and yet they end up in very ethnically homogeneous clusters eventually, which we argue could be a side effect of some of these mechanisms. So if people who move into this community together, who are a long-lasting couple, are married, they often come from the same cultural background, even if only one of the partners has maybe small homophily preferences. This might lead to the fact if people agree on their partner choices, that this level of homophily is somewhat amplified. So this is like a network level outcome, this kind of mild segregation, I would say, which is not immediately visible if you just look at individuals, people homophily, and yet it matters quite a lot. So if you're a person somewhere down here in this cluster, it's maybe very hard to actually get in contact with people from this cluster up there. So the network itself changes opportunities, and the network also constrains potentially how people can express their preferences. Similar example from this famous paper of Peter Berman, Moody, Stovall. Again, this is an expression of preferences. This is a dating pattern, sexual contact relations in a high school. People choose their partners. There's a mutual agreement process based on two people's individual preferences. And on the network level, you do see some structure that is maybe meaningful to people in a very different context. So this study focused a lot on mental health questions. And of course, it matters whether you're a person with 2 or 3 partners that is in the center of the network versus the periphery potentially when it comes to health-related outcomes. So again, we have, here we go. So I'm using as Enrico called it the somewhat refined version of the Coleman boat, focusing on networks. So we do have changes in networks. The network itself creates opportunities or constrains the way how individuals can express their preferences, for example, through tie formation. And these individual processes combine then could explain how the network changes through time. So we have these two different levels, the individual level and the network level. And well, Karoy said earlier that we are often interested in those large-scale consequences that go beyond networks. I would argue that a network can actually often serve as a reasonable model for something on a larger scale. So even if we collect data often in specific contexts, the things that you mentioned, like overarching level of cooperation, of segregation, of conflict, polarization, I will talk about later. All these things we can maybe map reasonably well in a network. And of course, we can think of a network as something being a bit larger than this student housing community that I mentioned earlier. Okay, done with the meta level. I'm going to talk a little bit about an empirical work where I want to show how we can try to study those different levels. The network level I will call the macro level, the individual tie change decision level, or expressed behavior as the micro level, how we can jointly study this and try to link it. And I picked this paper because I figured that that political polarization is a topic that is of high importance in the ABM community. But of course, it's an important topic to everyone. So this is a data set where actually we do not expect a high level of polarization. So this is a community of first-year undergraduate students, and those were regularly surveyed over the course of 3 years about their friendship relations. So we see these circles are students. These are symmetrized ties for visualization purposes. So people form friendships. So there are some clusters, friendship clusters here. And all, at the same time, we ask them about in how much they agree with specific policy statements. So they can, it's measured on a 7-point Likert scale, but in principle, they can agree or disagree with certain statements. So this is a trichotomized way of thinking about those statements. So for example, people might have an opinion on abortion. So they might agree that that women have free access to abortion, or they might disagree. So there are certain items, and many of those items are a bit more specific to the Swiss context in which data were collected. Also a bit more relevant to the student setting. So there are questions about tuition fees, about bike lanes in the city that these data were collected in. But in principle, there are some items where people rather disagree, some items that people rather agree with, and some items that are somewhat debated. And we're looking at these two networks, or it's actually 3 networks. So we have students and their friendship ties, and then students and their positive or negative attitudes, relations with those policy items. We look into this as a dynamic network model from a dynamic perspective. So, but what we can say is that we do not only have questions on the micro level, but we actually have questions potentially on 3 different levels. So we can ask the question, is an empirically observed network like this one, is it polarized at all? And if so, to what degree? And potentially, does the level of polarization change through time? So we are now looking into the more like the Karoy point of view, the society level outcomes. But of course, we can also think of polarization as a micro level process. So where people become similar to those they are tied to, or maybe become less similar to those they are not tied to, like in Andreas' presentation earlier. Is there clustering around certain topics? Do certain topics usually cluster together? These are all micro level processes on these different networks that we're looking into. And if we try to test specific hypotheses on this behavior level, so how people create friendships and whether they take into account policy similarity or agreement in terms of political views, or whether when they change their opinions about political items, take their social network into account. If we express this with a micro level model, and that will be a stochastic actor model later, we can then finally ask the question, does the model itself then represent well what we observe on the network level? And of course, we can also think of this as 3 levels of statistical tests, where we first of all can ask the question whether a community is polarized at all. We look into 2 different dimensions of polarization. So Andreas talked about the effective polarization, so whether you're more likely to like people you're similar to or dislike people you are dissimilar to. In our context, we call it relational polarization because we're actually looking into relations, into specific friendship ties, whether people are more likely to be friends with those they agree with and not to be friends with those they disagree with. And second dimension, ideological polarization, whether in general there's like we can partition the network into parts where everyone on the one part would agree with certain policy items but disagree with others, and vice versa. People on the other side would oppose the items that the people in the first cluster agree with, and agree with the items that the people in the first cluster disagree. So, two different dimensions. I'm not going to go into detail about the network level measure. I'm just going to give a bit of an intuition, but then we can also ask questions about whether we find significant evidence for specific mechanisms. And in this case, it's homophily, it's social influence, it's clustering based on similar others. And then finally, the question whether we find whether the micromodel adequately explains the observed macro level network features. Okay. So just very briefly about the two dimensions of polarization that we're going to look into. I'm spare you well, there will be a few formulas, but just to get the intuition. So a network which is ideologically polarized would mean that if person A and person B agree on one item, and then person A, well, they disagree with one item, person A disagrees with the second item, then also this person here would disagree. So they're basically, whenever they agree once, they would also agree twice. And those people down here, they agree once, and then also they agree on the other items. So basically there's a complete clustering into people fully agreeing or disagreeing with certain items. And at the same time, there's this dimension where people, and the black ties here would be, for example, something like friendship. Whenever they're friends with someone, they agree with their friends exactly on items. Here, two people agree on with an item, so they're pro bicycle lanes or they're against bicycle lanes in case of the other friendship. And then, of course, this is the case where you maximize both levels of ideological and relational polarization. So the general idea is that that we are counting network structures. So ideological polarization refers to force cycles in the two-mode network. So if two people agree on one item, do they agree on a second item? So we count so there are two different subdimensions, and maybe I just jump to the intuition. So the first dimension is maximum if two people agree twice with everyone they agree with once, and also they disagree twice with someone if they disagree once, in terms of two people and two policy items. And the relational part is all about centered these friendship ties. So it's maximal if you are tied to everyone you agree with, and if you're not tied to everyone you disagree with. So basically, on each dimension, we take the mean of this attraction and repulsion idea, and then we come up with two dimensions. Ideological part is the clustering around certain issue items. Relational part is whether you agree with your friends, and we have a simple metric that is, if there's no such association, it is expected to be 0.5. So it ranges from 0 to 1. This is the midpoint. And if you are on the top right of the 0.5, that means that the network is slightly ideologically polarized in our case, because the index goes all the way up to 1, and slightly relationally polarized. So if we just look at the, let's say, effect sizes, we see that on both dimensions, the network is slightly polarized, but the numbers seem not to be so large. And also there are no clear trends in whether there's an increase or decrease of polarization according to different dimensions. So these are from two different networks where we did these tests. But then the question, of course, is, are these differences from this midpoint, are they significant? And here we can apply a test that is similar to what Jen just described, like a permutation test. It's or like a rewiring test. We take the network, we take keep the structure in both the friendship network and in the two-mode network, but we destroy the association between them through permutations. And in these permuted networks, on average, they are on this midpoint as expected. And it appears that in most cases, this empirically observed value is very unlikely to be generated from this distribution. So we are like have a p-value that is very small. So we find very strong evidence that while the level of polarization may be small, and now I'm referring to this value of 0.56, which is on a scale from 0 to 1, it is statistically significant. So we find some significant level of polarization on a very mild level, I would say. And then we can ask the question about the processes, how this comes about. And of course, here we can think about different processes, such as the dashed line would always be like the dependent variable, whether people are more likely to become to be friends with people they agree with, whether they're less likely to be friends with people they disagree with. Here is whether they're more likely to agree with something that their friends agree with, and whether they are less likely to disagree with something that their friends disagree with. And then finally, these two forms of latent clustering, whether if there are two people who agree on one item, whether they are more likely to agree also on the second item. So whether this person on the left would be more likely to agree to an item if this is agreed with by a person who agrees with another item that this person agrees with. I hope that it's clear, and the other way around. So whether it's more likely that they would disagree with or agree with something that someone disagrees with who is otherwise also of different opinions than them. So reflecting these two ideas of attraction and repulsion, becoming similar to similar others and dissimilar to dissimilar others. We do this with a stochastic actor-oriented model. This has been mentioned a couple of times. I put in those slides just in case someone wants to ask a few questions later. So basically, we have a micro-level model that controls for many things besides those hypothesized effects, things like clustering, reciprocity, degree distributions, so many things. And on top, we can test the residual effect of those hypotheses, and we do find evidence for some. So, for example, people tend to be more likely to be friends, become and be friends with people they're similar with. They're not significantly less likely to be friends with people they disagree with. In one cohort, they tend to become more similar to their friends, and the other, there's no significant effect. And there's no significant effect that they would not that they would not choose opinions that are different from their friends. And then we have a strong significant effect for those two types of clustering. So we do find some hypotheses for those network mechanisms, and referring back to Federico, these are not causal mechanisms, because each of those mechanisms can incorporate many things. If we call this social influence, maybe this we can even think of many causal ways how social influence comes about. It's more like a reflection that is in line with the theoretical prediction of a social influence model, but it's not like a causal proof of the existence of social influence. So the final thing is that we can do is kind of assessing whether the model works, which is, you can think of this as a model fit test, but it's also, one can think of this as a link between this micro model and the macro level outcome, because the macro level outcome in this case is immediately like the macro level measurement of polarization, whereas these micro level mechanisms are more like the behavior representation. And this was the midpoint for those baseline models. Here we see that the midpoint of the fully specified models is much closer to those empirically observed values, and in many cases, those empirically observed values seem like reasonable outcomes of the stochastic actor-oriented model, of this micro level process that includes all those mechanisms for influence, homopoly, and other effects. So just briefly revisiting the three levels of questions about polarization. So we did see that the undergrad student network was moderately polarized along the relational and ideological dimension. We also found some evidence for processes of homopoly, social influence, and latent opinion clustering. And we could also conclude that the micro model could reasonably reproduce those macro level features, particularly compared to this baseline permutation. It is unclear whether it sufficiently captures trends through time and whether it's suitable working for all waves, assuming that the mechanisms stay constant through the whole data collection. So I put some final thoughts on the slides, on the final slide. Maybe I'm just mentioning a few main points. So it's actually fun to look at those macro features, micro level models jointly in longitudinal empirical settings. There are these 3 levels of research question that I think is interesting. And I want to point out, this is somewhat similar to what we tell students what they should do, like doing proper data description, doing model assessment. However, I would argue that this goes a bit further because we're actually doing tests on each level and we're looking into the same phenomenon, both from the network level and the behavioral level, and trying to study this jointly. It's maybe a comment that the polarization, and this was came up in, I think also in Andreas' talk earlier. Of course, in empirical work, we do not always find these very strong extreme outcomes like consensus versus bipolarization. It's quite difficult to study these subtle intermediate outcomes in polarization processes. And it's also not so straightforward to model and theorize about, because one obvious thing would be that we could now use this final step of the simulation model maybe as a starting point for thought experiments. Let's double this parameter. Let's remove this mechanism out. Well, Christian has been working on this a lot. I haven't fully gotten my head around how we can do this in the most meaningful way. Maybe I'm gonna learn a bit more about this later. And I think one important thing is that all these very subtle mechanisms are, of course, embedded in a variety of other network mechanisms that can be much more prominent and much more pronounced than the specific mechanisms we theorized about. Okay, thanks a lot.
So he has been perfect. So in time, so we have 5 minutes for question and answer.
With regard to the topics or items that you are considering, and I think it's also very fascinating that you didn't have any kind of assumption about this in the models, but they might be related to each other to a different extent. So that if there is an expert to evaluate these topics, that probably finds that okay, this is almost the same. But also they might be differentially important for the individual. So like they might have salience, for instance.
Yeah.
So did you consider to integrate a topic similarity or salience into this kind of analysis?
Yes, it's a very good point. Obviously, we treat this in a very simple, homogeneous way in this model. We did some descriptions on those items, like how they cluster, how they related to one another. We always played with this thought experiment. How would our results change if we had just asked the same item twice or 3 times or 5 times, kind of inducing some form of similarity? I think there's a lot to be done. Also, we could actually ask questions about how well the model fits for specific items versus others. And well, in the abstract, I promised a second empirical paper until I realized it's a bit too much, where we actually look into the specific items and how they differ in a space. But it's a very good point. Correct.
Yeah, great way to model polarization. Very interesting. And then I'm wondering what would happen if you would treat the topic just as a behavioral variable, right? So a dynamic behavioral variable. And then you could estimate a more standard Archenna model, which is exactly what my PhD student has done on your data. Which you probably are aware of, with the same items. And he doesn't find any influence in selection. And his conclusion is that's because there's not much difference at all going on, which is more or less also what you are saying, but you are able to pick these dynamics up. So did you compare those modeling strategies? And
yeah, so I think I'm aware of this paper.
yeah, luckily.
we had quite some chats about data and interpretation. I think we have, for example, we have indeed nodal variables and where people put themselves on the left to right spectrum. I think in general, if you have additional information on multiple items, I think it's nicer, and also you use more information if you express this in a two-mode network, two-mode approach. And I think the logic is very similar to the social behavior versus network model that Christian proposed, because those are two co-evolving processes. It's just if you aggregate this on a, let's say, you do some latent score, you lose a lot of information. And I think this allows us to probably be a bit more specific about the test. I remember that, well, with this nodal variables like left, right, self-placement, there are also some kind of feelings of warmth and coldness towards certain positions. Well, there's indeed not so much in the data. And as I said at the beginning, this is a first-year undergraduate program, so not really the empirical setting where you expect like a social media type of culture war going on. But there are more salient topics. So these people are more likely to talk about which study programs to take, maybe about free time activities. I don't know what students do in the first semester. Such a time for bars where you go out to. So there are a lot more salient topics than these political items. And still, there's some weak evidence that both the social network follows some similarity patterns, and also that there are changes to this similarity patterns that is affected by the social ties. But it's indeed very, very weak. And if you look at the effect size and also at the network level of polarization that I've shown, both are very small. But there is some evidence that it's there.
There was a question, last one from.
Okay, well, actually, some of my questions have already been asked, so that's great. Yeah, I was wondering about attitudes towards groups. Groups. So I think the issues you have in there are more like political issues. Should we build a bike lane here or something like that? Did you consider to also take that into account? How do students think about other groups, and how would that feed back into the interactions?
Yes, we have thought about this, not in the context of this study. So, I mean, this is a ethnically relatively homogeneous community, which has to do with the fact that this is a German-speaking undergraduate program. So there are some nationality differences, but even those are relatively subtle because most people have the same language background. We do have, not just mentioning things, if you have a student who might be interested in that. We have a couple of questions on gender-related attitudes. So it's a technical program, and there's a female minority. We are, for example, asking questions about perceptions of genders in terms of certain outcomes. And we do have which is not like a group in an ethnic versus demographic group, but we have this question about groups that people feel they are a member of. So they could name up to 5 groups and also name other people who are members of these groups. And we also ask the question about groups that they are not members of. So it's more like an emergent type of group potentially. So these could be groups that are centered around many things like free time activities, preferences, maybe demographic attributes. We didn't specify this, but we do have this measure in the data, but it hasn't been studied in this context with political attitudes or anything related.
Okay, thanks.
Thank you.
Okay, excellent. Thank you, Chris.
Thanks a lot.
So lunchtime. Yeah. And we'll be back at